Hello everyone, my name is Dmitry Zasukhin. My work is about evaluation of zeolite acidity by 31 phosphorus mass NMR spectroscopy of adsorbed phosphine oxides. Commonly, the active sites in zeolites are Bronsted and Lewis acid sites. In slide, you can see its approximate structure. Such acid sites characteristics as nature, strength, amount, and accessibility allows to predicting the catalytic activity of catalysts. It is important because different acid sites provide different catalytic reactions. However, existing method for studying acidity don't provide answer to all questions. And 31 phosphorus mass NMR of adsorbed phosphorus-containing prop molecules can be a promising method to solving such problem. So the aim of my work is the creation of a universal method for the quantity determination of various acid sites in zeolite using 31P mass NMR spectroscopy of adsorbed trialkyl phosphine oxides. We used oxides of 3-methylphosphine, 3N-butylphosphine, and 3N-octylphosphine in our work. Nextly, I will refer to them as TMPO, TBPO, and TOPO, respectively. The slide also shows an example of the interaction between these prop molecules and acid sites. We decided to use these molecules which have different size because it is necessary for the further separation of acid sites by accessibility and localization. We used commercially available beer zeolites with different silica to aluminum ratio of 25 and 150. Also, we use dealuminated zeolite beta and pure silica beer zeolite. Here you can see adsorption technique that we used in our work. Zeolite powder placed in a glass ampoule and calcined in a vacuum line at 400 degrees for 14 hours. The next step is impregnation of the sample with a solution of prop molecules in dichloromethane in a dry glow box. Then the solvent was removed on a vacuum line and the ampoule with the sample was sealed. After that, the sample was activated in a muffle furnace at a temperature of 200 degrees for 2 hours to complete diffusion of prop molecules inside the crystals. Finally, the ampoule with the sample was opened in a dry glow box. The sample was transferred in a standard 4mm mass NMR rotor and the spectra were recorded. Firstly, we provide some experiment with different prop molecules adsorbed on aluminum Br25 zeolite. The spectra you can see on the slide, and the amount of adsorbed substances is also indicated here. Based on the literature data, we identify the area of chemical shift in which the signal corresponding only to acid sites. Next, we integrate the spectra and normalize general integral by the amount of adsorbed substances. It turned out that the total acidity obtained by this method significantly different with total acidity obtained by infrared spectroscopy of adsorbed pyridine and theoretical amount of aluminum in the structure. More important that reproducing of the experiments lead to a large scatter in the observed result. This can be seen from the large value of relative error. After analyzing the result, we identify three main sources of errors. It's the loss of probe molecules during sample preparation, incomplete relaxation of nuclei during spectral registration, and incorrect integration of the spectra. To solve this problem, we first decide to use standards. As standard material, we consider substances such as inorganic phosphate, alpha and SAPO materials, and metal phosphides. We decided to independently use two versions of standard, external and internal. The external standard have very simple and general requirements. It's stability and established composition, which mean a known molecular weight. For internal substance, additional requirements are necessary. First, it's a suitable chemical shift. Second, it's inertness with respect to probe molecules and zeolite. And finally, a small specific surface area. Among the different external and internal standards investigated in our work, ammonium hydrophosphides, gallium phosphates, and aluminum phosphate with tridimate structure are proposed as external standard. What is more, alpha-tridimite is selected as the internal standard. Although the use of external standard is found to be simpler, but the application of the internal standard is concluded to be more reliable. It's well known that to obtain quantitative NMR, complete relaxation of nuclei is necessary. In the course of addition studies, it turned out that not all phosphorus nuclei have enough time to fully relax when we record our spectrum. For example, in the slide, you can see the spectra of mixture TOPO, pure, and alpha-tridimite. From the spectra, it's possible to determine the relaxation time, and for TOPO, it's about 300 seconds, and for alpha-tridimite, it's about 415 seconds. The accurate measurement of spin lattice relaxation time for all individual and adsorbed probe molecules, as well as for the reference compound, suggests that for quantitative measurements of adsorbed probe molecules, we need to register spectra with recycle delay time for 40 seconds. But when we use internal standard alpha-tridimite, we need to register spectra with recycle delay time more than 2050 seconds. Another important source of errors which we faced is the baseline distortion observed in single pulse, one pulse experience. Subjectivity of the baseline correction make it difficult to integrate spectra, especially spinning sidebands. To solve this problem, we recorded the spectra with Han echo sequence because no baseline distortion is observed in them. And the chemical shift anisotropy parameter is in the spectrum the same as the one pulse sequence. So the ratio between sum of central line and spinning sidebands intensity and only central line intensity is the same as a one pulse sequence. Then we multiply the intensity of central line obtained from one pulse sequence to this constant to obtain quantitative truly integral. So final equation is here. In fact, it is proportion between intensity multiplying on obtained constant and normalize of on number of scans. But at the same time, we take into account all the corrections described above. Then we try to calculate the total acidity of one sample using different standards. And we can see that the result obtained with different standards, internal alpha-tridimate and different external standards, is nearly the same. Using this calculation method allows us to recalculate the result obtained earlier. So we observe a decrease in the relative error. Comparing the data obtained by this technique with amount of acidity obtained by infrared spectroscopy of adsorbed pyridine and theoretical amount of aluminum allows us to draw the following conclusions. TMPO probe molecules has a smaller size. It can easier enter the pores of beer zeolite and can interact with all its acid sites. The number of acid sites measured by TMPO correspond to the content of aluminum in the sample. The number of acid sites measured by TBPO consider with the data obtained by IR spectroscopy of adsorbed pyridine. Most probably, TBPO can enter the pore system of zeolite, but it cannot measure all the sites owing to spherical hindrances. Oh, sorry. TOPO molecules has the biggest size and most probably cannot enter the pores of zeolite. It measured the site at the outer surface of the crystals, or surface of the crystals. So, in order to obtain information about the observed signal, we decided to compare the spectra of TBPO adsorbed on different beer zeolites. Here you can see the spectra. Blue and red spectra are related to two aluminum beer zeolites with different silica to aluminum ratio, 25 and 150. Purple spectra it's to contribute to dealuminated zeolite, and green spectra is pure silica zeolite. The intensity of signal located in this red area decrease with a decrease in the amount of aluminum in the sample. In the blue area, signal related to physical adsorbed and individual probe molecules are located. The changes in green, this green area, corresponds to the changes in this region related to difference in IR spectra of silanol vibrations region. Comparison to the results obtained by these two methods allows us to attribute the signal in this region to the different silanol groups, internal and external. And finally, we turn to quantification the spectra. For sample of beer zeolite contain little amount of aluminum. The results obtained would correlate with amount of alumina in the structure. When we see on this obtained of the sample with big amount of aluminum, we can see that theoretical amount is much more than number we obtained. This can attribute it to the spherical hindrances of TBPO in the structure. So in the slide, results and discussion, results and conclusions is here. A technique for determining acid sites based on phosphorus NMR spectroscopy of adsorbed molecules is proposed. The use of standard is necessary to obtain reliable information about the number of acid sites. It is shown that for a correct quantities assessment of probe molecules, it is necessary to know the relaxation time. Using TMPO probe allows you to determine the active sites throughout the volume of crystals. Using TOPO probe allows you to determine the acidity located on the outer surface. and the results obtained with TDPO probe molecules correlated well with IR results observed pyridine and make it possible to estimate the amount of various cyanoyl groups. So thank you for your attention. That's it.
Thank you very much. So we have time for maybe one question. And once again, Sergey Vasilyev, please don't hesitate to ask questions.
I have a small suggestion about long relaxation time. And I wanted first ask how many scans do you apply for phosphorus to obtain the spectra?
So now, when we register spectra with full relaxation of internal standard, we obtain about 8 scans.
8. You can decrease the length of the pulse, so the relaxation is exponential, and you can gain much more signal to noise ratio in shorter times, and also you will obtain quantitative spectra because your signal to noise ratio in the spectra is very good. So you can obtain the spectra with much smaller pulse, for example, 5 degrees. So your relaxation delay can be lowered much. Sometimes this is called the Ernst formula for the repetition period.
We know about it. It's current our work. We know about Ernst angle, and right now we try to use it in our work. Yes, but now we don't use it until today.
Thank you.
Okay, Vladimir Chizhik.
Yes, yes. Which mass frequency do you use in your spectrometer, and which is line width in statics?
Okay, when we use internal standard, mass frequency is 10 kilohertz. When we don't use internal standard, is 12 kilohertz.
It is very close.
Yeah, but just a second. In the slide, you can see the region where signals attributed to probe molecules on acid sites are located. And when we use internal standard, we should decrease rotation rate to prevent overlapping of spinning sidebands with signals.
Yeah.
Yes. Could you repeat your second question?
No, it's 2. Which frequency and which line width?
Line width, it's about 50. I don't remember.
Okay.
I don't remember.
So thank you very much for